Next speaker is Tobias Nießen on finding counterexamples to for-order exist hyperproperties.
Maybe it's better to.
And then coffee.
Okay. So put it here. Okay, that should be fine. Try
Thank
speaking.
you. Hey, seems to work.
And if you feel like it's not working, just check that it's there.
Okay,
and
thank
turn
you.
it off.
Okay, hey everyone, my name is Tobias, and yeah, this is probably going to be apparently one of the very few talks that have pretty much nothing to do with incorrectness logic or any of these similar derived logics. So yeah, me and Georg, we are working on a kind of practical way of actually finding counterexamples when certain hyperproperties don't hold. So let's talk very briefly about what my understanding of incorrectness is, because that is a much broader sense than just incorrectness logic. So for us, what we think of incorrectness, at least recently in our research, is whenever we approximate a system and we try to do an under-approximation, and then we find something in this approximation that is not allowed by the specification, then we prove incorrectness, right? That's exactly what incorrectness logic does. That's what most of the talks today have been about. It's just a very general way of looking at this problem. So instead of over-approximating things and then trying to prove correctness, what this entire workshop is about is kind of under-approximating and then proving incorrectness, right? So we are looking at a particular class of hyperproperties which have significant relevance in practice, but which are unfortunately challenging in this area. So very briefly, what hyperproperties are in a very intuitive sense is it's properties that you can't prove or disprove by only looking at single execution traces of any system, whether that's hardware or software, infinitely many states or not. If you only look at one trace, you cannot prove or disprove these properties. That's a very informal definition, but it really depends on the logic that you use. So one very simple example here is what we call observational determinism, which essentially just says a system is observationally deterministic if for every pair of execution traces, if the inputs are the same, the outputs must be the same. Note that this is very different from a system actually being deterministic or not. We don't care if the system internally behaves deterministically or not. We only care about what we see from the outside. That is quite the significant difference, because if we looked at the internals and it behaved non-deterministically, we could decide that using a single trace only. But here we actually need pairs of traces of the same system to decide that. And yeah, so we can quantify over trace variables, which is much more powerful than only quantifying over the value of program variables or so. And in many cases, these properties, when we only have universal quantifiers, we can reduce that quite simply, or well, depending on how efficient we want to make it, in a quite complicated way, to the verification of single trace properties. So as long as we don't have any quantifier alternation or so, that works quite well. And many under-approximate methods work as well. For example, bounded model checking, which is inherently under-approximate, it only finds bugs. It never proves, well, there are certain cases when it can prove that no bugs exist if you add certain assertions to the formulas. But in general, it's more convenient for finding bugs than for proving correctness. Now, things get much, much worse if we had quantifier alternation, as usual in any kind of higher order logic. So, for example, refinement, API refinement, is also sometimes called the correctness of implementation, says that if you have two different programs, P and Q, and you want to see if P refines Q, then you ask, if I execute P and it gives me for some input, some output, does the original program Q have some execution? Does there exist some trace for the other program Q that would have given me the same result? So, for example, if you draw a random integer, it does not refine drawing randomly from the set of natural numbers, because the integers are a superset of the natural numbers. But the other way around, if you only draw from natural numbers, it's a refinement of drawing from integers. So, yeah, unsurprisingly, verifying these properties is much more challenging. And what we kind of want to do instead, because most of the approaches to verifying these properties, if they work at all, if the property doesn't hold, and let's be honest, we have this workshop because most software has bugs. In most cases, the property that we are trying to verify does not hold. And most existing approaches in this area, if verification fails, they just tell you that. They either don't terminate or they tell you, well, I couldn't prove the property, good luck. And what we want to do instead is if the property doesn't hold, we want to give the user a specific counterexample explaining why it doesn't hold. And the existing approaches to verification of these can roughly be categorized in these four categories, where for one, we have strategy-based approaches. These are usually based on game theory, where for the universal traces, you have players, and for the existential traces, you have players. and the players representing the existential traces have to try to make moves to counteract whatever evil action the universal traces are trying to do. And if there's a winning strategy for the existential traces, then the property holds. This is inherently incomplete because the existential players cannot see the future of the universal players. So there's a way using prophecy variables to make this complete, but then it really doesn't scale anymore. It effectively becomes useless. Then there are automata-based approaches, which are great. They are very convenient, but they simply do not work for infinite state systems. They are strictly limited to finite state systems. And since our primary application domain is supposed to be software, we kind of have to be able to argue about it. We have to be able to reason about infinite state systems. Then, of course, what most of this workshop has been about is hostile logics, and there are a few relational hostile logics that can reason about these properties and then can do verification. But those that do verification usually run into the usual problems with the loop invariance, for example. So the state-of-the-art tool, there are ORHLE, whatever the acronym stands for. The paper doesn't actually say. It requires every loop to be annotated with a loop invariant. So automation is really challenging in most of these hostile logics. And there are some under-approximating relational hostile logics. But yeah, as far as I'm aware, nobody has actually implemented them in any way that works in practice. And then lastly, of course, you can always reduce to QBF, but that again doesn't work for infinite state systems because then you're constrained to a finite number of Boolean variables. And yeah, completeness also, of course, as with bounded model checking, is not guaranteed. So instead, what we want to, oh yeah, just for reference for anyone watching the recording, this is what the table was based on, so please read all of these if you don't trust me. So logics are complicated, and especially for software, we want to be able to deal with infinitely many states, we want to deal with variables over infinite domains, and we want to deal with asynchronous behavior. So this logic, hyper-LTL, it extends hyper-LTL. It is from a 2022 paper by Finkbeiner and Beutner, software verification beyond case safety. And yeah, it's a great logic, but it makes things horribly complicated. It is very convenient for the user because it lifts a lot of complexity from the actual formula to the implementation of the solver. So essentially what it does to implement asynchronous behavior is it maps whatever observations you have in your program. You can define arbitrary observation points within your system, and then it simply projects those locations onto a new set of infinite traces. So your traces become shorter if you have fewer observation points than every single point on your trace. But yeah, it maps infinite traces with a potentially infinite, no, it has to be an infinite number of observation points onto a set of shorter traces that then simply consist of the observation points. So it kind of synchronizes your observations for you onto a shorter set of traces. And now, very briefly, I know most of you are familiar with this just because we use symbolic execution a lot. I just want to go very briefly over a very simple version of symbolic execution. So all it does is very stupid. It goes through all paths in your program, and then it checks if it's feasible using an SMT solver or set solver or whatever you want to use for the theory. And yeah, in this case, for example, only 3 out of 4 paths are feasible, and the symbolic execution engine would only explore those paths and would give up on the infeasible paths. So it scales quite well. There are multiple tools that implement it. KLEE, I don't know how it's supposed to be pronounced, works super well. But of course, it's all incorrectness based. It's all under approximate. It will never terminate if you have any unbounded loops or so. So works well in practice, but not in theory. So our approach is very similar. We essentially, I don't want to go into the details of the algorithm too much because it gets kind of tricky. But yeah, our approach is simply for the universally quantified traces, we use symbolic execution to pick traces, to pick paths. Traces would be too specific. Traces would already assign values to variables. We just care about paths at that point. Then we derive some constraints for the SMT solver from the path we have selected, essentially just all the conditions along that path that we get during symbolic execution. And then we use bounded model checking using an SMT solver, or if you really want to constrain yourself to finite state systems using a set solver, that solves a rather complicated query of a fixed structure. So one of the future goals is to optimize an SMT solver for this particular kind of query that we're giving it. And yeah, that will either give us a counterexample if that actually has if the bounded model checking instance holds, then we've actually found a counterexample because this, as you might notice, the eventually here is already the negation of the original property. So if that holds, then we found a counterexample. Otherwise, we need to refine our set of constraints to further limit the search that the SMT solver can do during this bounded model checking instance. And yeah, that part, refining C, is a very, very difficult problem that I'm not going to go into much. There's a lot of existing research on that. Essentially, you have to under-approximate the set of inputs that could lead to this spurious output. And yeah, that is, we've heard about weakest preconditions today, and it's a very difficult problem. But for some theories, for example, for linear integer arithmetic, it's decidable, and it actually terminates in that case. For other theories, not. So constraint solves to easy problems. And of course, when we do this, it sounds simple at first, but we do run into a bunch of problems. The first is that all of these temporal logics, like LTL, hyper-LTL, and O-hyper-LTL, they all assume you have infinite traces. They all assume, in the case of O-hyper-LTL, it's even worse. It assumes you have infinitely many observation points along your infinite traces. And of course, we can't have soundness when we reason using these logics if we only look at finite traces. And with symbolic execution and with bounded model checking, of course, we only ever get finite traces that we consider. So there are some approaches to this. There's from Armin Biere, there's an adaptation of LTL from 1999 that defines bounded semantics, but we cannot adapt that to the hypersetting at all. Then there's LTLF, which works surprisingly entirely differently than the bounded semantics for LTL that Biere defined. You can have global properties that hold even on finite traces, which is not true in any of the other logics here. And yeah, then there is another paper from 2021 where there's 4 reinterpretations of hyper-LTL. There's an optimistic semantic, there's a pessimistic semantic, there's a halting optimistic, and there's a halting pessimistic semantic defined in that paper. Unfortunately, all those still don't really work for our case because we want to do software that has asynchronous properties and also infinitely many states. So we want to have arbitrary predicates from our theory and our formulas, and we want to be able to synchronize asynchronous behavior. So for O-hyper-LTL, as I said already, we have infinitely many observation points that the logic assumes, which makes it difficult to redefine these semantics properly. And we also have the big problem of asynchronous termination. We had a talk earlier today about finding out if something is not going to terminate. And sometimes you want that, but often you also want your algorithm to terminate. For example, RHLE, one of the state-of-the-art Hua logics for relational properties, it assumes that your program always terminates in one output state, and yeah, it proves properties about that. On the other hand, O-hyper-LTL was designed for infinite traces that never terminate, and our goal is kind of to support both. We want to have a tool that can handle terminating and non-terminating programs with different behaviors. So yeah, this was one of the problems we faced, properly defining semantics so that our counterexamples would actually be sound. The second problem is what we call divergence. It happens quite quickly. If you look at this very simple example program, there's always an integer b such that there is a longer trace to reach the observation point. If you try to apply bounded model checking here and you're drawing random natural numbers, there's no bound here, right? Let's say it's Python or horrible JavaScript big integers or so. There's no upper bound on the length of the trace here, even though there's just one observation. So we know it's always going to terminate, but bounded model checking is never going to find a bound that does that. You can try to apply acceleration, that's what we do, but yeah, for the basic algorithm, this is a horrible case. Third problem, and this one is actually rather rare. We only encounter this in theory. We haven't actually come across any benchmarks that would run into this. There are instances where there simply is no, and now this is a rather complicated way of looking at it, there's no finite set of finite traces that would prove that something doesn't hold here. Now, we can see, of course, this property doesn't hold because there's always an execution where eventually A equals B. But yeah, the bounded model checking again cannot prove this because B can be arbitrarily large. That means you need to look at arbitrarily many executions. So either you need an infinite set of finite traces, which we can't do using model checking, at least not in this way, because we need infinitely many different paths, not just traces, or we need one infinite trace, and we can't reason about that. Fourth problem, what actually is the counterexample to an existential quantifier? For the universal quantifier, it's easy. We give the user one concrete trace. But yeah, the other part for the existential quantifier, we need to kind of produce a certificate that it doesn't hold. And just giving the user the proof that the SMT solver gave us is kind of useless to the user because the SMT formula that we give to the solver is insanely complex. It has little to do with the original input. So now we need to retranslate that proof to the original input semantic. And yeah, this is also work in progress. We don't have much here to show yet. But yeah, we can give you the trace, but the certificate is actually quite difficult to achieve. If you look at the opposite case, if you look at verifying for all exists properties, what people usually do is they require the synthesis of a witness function so that for every input, the witness function then gives you the existentially quantified variable that belongs to that trace. The problem with that is even in the finite state system, it's double exponential time hard. So yeah, in infinite state systems, it's just never going to work. Yeah, just very briefly, there are some interesting properties that require more than 2 quantifiers, most notably perhaps generalized non-interference, which is super important for security properties. I don't want to, for time reasons, I don't want to get into the details too much, but essentially you say for every 2 executions that share nothing, there is a third execution that shares the low security input with the first trace and the high security input with the second trace, and that produces an output that is indistinguishable from the first trace. If you're looking into probabilistic programming or so, you'll say that this is not a good specification at all, but if we're only looking at possible outcomes, then it's an accurate characterization. So for that, of course, we have our base case where we have 1 quantifier. If you remove the universal quantifiers, then it just degenerates into bounded model checking. Then the symbolic execution engine will just produce a single path and nothing else. If you remove all the existential quantifiers, it degenerates into symbolic execution. The bounded model checking becomes trivial. And yeah, if you have more than one of either, then our implementation does a product construction, which in the case of verification would be horrible because most verification algorithms fall apart once you do product construction, and that's what most of the research for all safety, for all case safety properties is about. But yeah, in our case, since we only do symbolic execution and bounded model checking, it worked quite well. And yeah, lastly, we took 2 existing sets of benchmarks from the literature. This is from the Finkbeiner and Beutner paper from 2022. And yeah, surprisingly, it works quite well. All of these algorithms, all of these input instances, I should say, the property holds. There are no counterexamples that our algorithm could find. So when I mark something as green here with a check mark, it just means that our algorithm never terminates because it never finds a counterexample. You can constrain how many observations it should do, and then it terminates after that many observations, but of course not with any definite conclusion. There are 3 instances that diverge. Yeah, it's not really surprising. There are 3 cases where there's an infinite loop before an observation point, or an unbounded loop, I should say. And yeah, of course, in that case, our algorithm is not going to terminate. Still, surprisingly, it works in many cases, even though these are kind of trivial. There are no counterexamples. More interestingly, the set of benchmarks from the RHLE paper, 2022, I believe. These are more interesting. There are a bunch of examples here where we do produce counterexamples. Again, no certificate, but we kind of believe the SMT solver for now. And yeah, there's 2 cases that diverge. There's 5 cases that require division, which we haven't implemented yet because it makes the whole problem undecidable. The decision procedure doesn't terminate anymore. And yeah, 1 example that I haven't encoded yet because it's, I don't know how to fairly encode it because it's written in a way that is very complicated. But yeah, overall, the experimental results are quite good. And what we think, we kind of lifted the QBF approach to SMT, so to support infinite state systems, which is very cool. It also means that for some theories, of course, it's going to become undecidable very, very quickly. But to be fair, the whole problem, even for single trace, is undecidable. So yeah, and one advantage is that the incompleteness that we have here is quite, we can characterize it quite well. So we can define precisely for what input instances it will and for which it won't terminate. Modulo decision procedures. Yeah, thank you.
Thank you, Tobias.
Hi, thanks for the fantastic talk. Question, how deep can you enroll? So up to how many observation points can you enroll? Because your number of paths is growing exponentially, and very likely after 1, 2, 3 observation points, it's just intractable.
Yeah, it really depends. Sorry, this input, this language is horrible. It's not Lisp, it's just the best syntax highlighting I can get here. So this is an example here that branches exponentially. It's, yeah, again, don't pay too much attention to the actual syntax here, but both input programs here, 1A and 1B, have a while loop that counts up to 10, or one counts to 10, the other counts to 9, and, no, sorry, 1 to 11, 1 to, Yeah. Okay, so the first is non-deterministic and only increases x in some cases, and the other always increases the counter I, but only increases x in some cases, and then, yeah, we formulate queries about that. So this is actually quite slow. It's only branching, it only has a single observation point, but for the actual queries it has to construct 2 to the power of 10 paths for each SMT query, and then it has to do another 2 to the power of 10 such SMT queries, and yeah. So I can show you it's, if I remove the output statement, the debug output, it's going to be a few seconds, but even now it should terminate quite soon. So yeah, it really depends on the complexity of the input. We have some where we do 20. So from the Beutner paper for the hyper paper, there are some instances where we can do like 25 observation points because they don't do exponential branching. If you have a for loop, for example, you also have a linear. Now, if you don't have any branches within the loop, only exit conditions, it also stays linear, right? So yeah, it depends on how much time and memory you have.
One last question and then coffee.
So part of the success of the unary incorrectness is that you're in a way making the problem easier by changing a for all into an exist.
Mm-hmm.
Like you only have to traverse one path instead of many. And so in your case, you're taking a for all exists, and I guess you're sort of turning it into exist for all. So you have both quantifiers still, just in a different order. So did you find that that's in any way easier or harder, or it's like relatively similar?
Yes, so I think the main advantage is that using symbolic execution, you can guide the symbolic execution engine using heuristics towards interesting paths. I think that's one very big advantage, for example, compared to the QBF encoding, where you have to encode all the paths simultaneously. And also we do change it to an exists quantifier, but we do quantify over paths, not over traces anymore. So even if there are infinitely many traces, there's usually only a finite number of paths, at least of a certain length. For example, if you have variables of infinite domain, if you were to quantify over traces, you automatically, even if you have a single observation point in a finite length, the random sampling natural numbers example, for example, automatically gives you infinitely many traces, and quantifying over those is much more difficult than quantifying just over the paths and then letting the SMT solver figure out what variables to assign. So I think those 2 points are the major advantages here. I can't give you any performance numbers because, well, in most cases it doesn't terminate, or there's no comparison to any other tool. But yeah, I hope it's still somewhat convincing.
Thank you. Let's thank Tobias again.